Hello, my name is Pieter Gijsenbergh. I work at IMEC Belgium as an ultrasound characterization engineer. I'm also responsible for the development of several ultrasound application demonstrators. Today, I will talk to you about Polymer PMUT array for high bandwidth underwater communications, paper ID 6486. Today's presentation starts with an introduction before moving on to the design and fabrication of our system, followed by measurements and finally conclusions. Ultrasound transducers are characterized by the fact that they use pressure waves above a frequency of 20 kHz, outside of the audible domain for humans. Typical applications can be found in biomedical imaging, where it's commonly known as echography, the automotive industry, where a typical example are parking sensors, and also non-destructive testing. For communication purposes, however, they are much less widely used. This is due to the limited bandwidth at low frequency and the high attenuation at higher frequency. This is specifically challenging in liquid environments. Our proposed approach today is to combine discrete units with limited bandwidth to form a large fractional bandwidth system, typically around 20%, and this in a flexible, tunable, and large area technology. Target applications for this system are diver localization, professional swimmer tracking, and biomedical implant powering. Let's have a look at the design and fabrication of our devices. Everything starts with a single unit, a piezoelectric micromachined ultrasound transducer, or PMUT. Our devices are made in a display-compatible technology. This means they are completely polymer-based and fabricated on top of a glass substrate. They consist of a polyimide membrane coated with electrodes and a piezoelectric layer, PVDF in this case. The electrode and layer thicknesses were optimized, and the electrode ratios were also optimized to guarantee an optimal performance. The diameter of the photoresist cavity underneath the membrane is used as the main parameter to control the resonance frequency of the device. On the curve at the bottom of the slide, you can see that this frequency shifts downwards if the device is submerged in water. This is due to the extra mass that is added to the top of the membrane. Once we can make a single PMUT, we can also arrange them into arrays. This is exactly what we did for this system. An 11 by 11 matrix was composed of randomly distributed PMUT sizes. The three sizes that were chosen were diameters of 650, 700, and 750 micrometers. A random distribution is illustrated in the inset picture. Once the array is fabricated, a flexible PCB is bonded to the electrodes, and the entire system is then coated in a thin layer of parylene to protect the electrodes from the watery environment. Moving on now to the mechanical measurements. Mechanical measurements are performed using a laser Doppler vibrometer. First of all, in air, where each of the 121 individual elements are measured. On the curve on the right side of the slide, you can see resonance peaks for each of the three single unit cells that can be found in the matrix. 750 micrometer PMUT exhibit the lowest resonance frequency, but have a slightly higher response than 700 and 760 micrometer diameter PMUT, which have a higher resonance frequency. The individual resonance frequencies are found around 188, 210, and 240 kHz, each with a small variation due to process variations. The average bandwidth of each peak is only around 6 kHz, leading to 3 separate peaks when considering the entire array average. If we now put this array in a watery environment and remeasure all 121 elements, we can see that the 3 peaks have shifted down to lower frequencies, now between 60 and roughly 75 kHz. There is again some variation, and the average bandwidth is still around 5 kHz, so relatively unchanged. However, if now the array average is calculated, we can clearly distinguish one main peak around the center frequency of 66 kHz. Total bandwidth has been increased to 16 kHz. You can see this by the black curve on the right-hand side of the figure. Moving on to electrical measurements. When we connect the array to an impedance meter, we can characterize the impedance as well as the phase of the array in air and water. In the phase, we can distinguish 3 smooth maxima around the resonance frequencies of the individual elements. This is much less pronounced than when we look at a single PMUT in air, where a very clear phase peak is present. This is due to the variability between individual PMUTs due to the processing. When we look at the array in water, no phase peaks are present. And then finally, we get to the acoustic measurements, the main part of this presentation. First, let's have a look at the measurement setup. To generate the ultrasound signals, we need an arbitrary waveform generator. In my case, I use the Keysight 33522B, generating 5-cycle 10-volt bursts in a frequency range between 50 and 100 kHz. A hydrophone type Aquarian AS1 is used as the second element in the setup. For the readout of the signals, an oscilloscope is used. Typically, the hydrophone and the array are placed at a distance of 10 centimeters from each other. For the acoustic characterization, we first had a look at the receive performance of the PMUT. In this case, the hydrophone was used as the transmitter. Since the signals gathered by the PMUT array only generate a voltage between 50 and 300 microvolts, a 100-time averaging was set on the oscilloscope. Further processing of the signals was based on voltage peak-to-peak detection, using also the hydrophone transfer function in the process. We can see in the results on the right-hand side that there is a center peak around 63 kHz with a bandwidth of about 11 kHz. The peak sensitivity is in this case 0.23 microvolt per Pascal. A second peak closer to 90 kHz can also be observed, but in general there is a downward slope of the reception sensitivity towards higher frequencies. When we have a look at the transmit response, this time the PMUT array is used in transmit while the hydrophone is used as the receiver. Processing of the signals is done in the same way based on peak-to-peak detection and including the hydrophone transfer function. This time we observe a center frequency around 62 kHz, but again with a bandwidth slightly over 11 kHz. The peak sensitivity in transmit mode for this array is 1.6 Pascal per volt. Once again, a secondary peak is observed close to 90 kHz, but in general, a downward trend is also perceived towards higher frequencies. Which conclusions can we now draw from this? When we overlay the receive, transmit, and mechanical characterization graphs, we can see that there is a strong correlation between all of them. However, the acoustic performance peak is not as wide as the mechanical peak observed by the laser Doppler vibrometer measurements. In general, the acoustic center frequency can be located around 63 kHz with a total acoustic bandwidth of about 11 kHz, either a fractional bandwidth of 18%, slightly below the 20% we set out to achieve. The declining acoustic response can be attributed to the higher attenuation at higher frequencies, hydrophone response function errors, or other circumstances. Solutions for this can be to change the PMUT distribution throughout the array, to increase the array size, or to have a less random composition, for example, by including more smaller PMUT to better cover the high frequency range of the sensitivity. Additional experimentation with this system was performed in a 4 meter by 2.5 meter pool. 12-volt peak-to-peak linear chirps were used as inputs to the PMUT array, and an Aquarian H1C hydrophone was used as the receiver. As you can see on the graph on the right-hand side, these tests showed that the signal-to-noise ratio above 10 kHz is still achieved at a distance of almost 5 meters. This is very promising for future applications. The work presented in this presentation today was performed as part of the EU-funded Horizon 2020 program via an Excel joint undertaking project called Silence. The references I used in this presentation today, as well as in the paper, can be seen on the right-hand side of the slide. And with that, I would like to thank you for your attention, and I'm open to any questions you may have. Thank you.